Welcome to the Deep Dive. We're here to really unpack the essential knowledge from our sources and give you those key insights. Today, we're diving into a group of elements that are, well, they're kind of the unseen architects of our world. Group 14. That means carbon, silicon, germanium, tin, and lead.
Yeah, and it's quite a lineup.
Absolutely. I mean, from the very basis of life to the chips in our phones, even the ground we walk on, these elements are just everywhere. Think about it. Carbon, the core of life. Silicon, fundamental to geology. And then tin and lead, metals we've known for ages. It's such an extraordinary range of properties in just one group. How can 5 elements be so different, yet so crucial?
That's exactly the question we'll dig into for you. Our goal here is simple. Guide you through the core ideas of Group 14 Inorganic Chemistry. We'll pull out the most important bits, explain the tricky concepts step by step. No visuals needed. We'll describe the structure so you can picture them. We want you to build a really solid understanding of this chemistry like we're just chatting about it.
Okay, sounds great. Let's get started and dive into this fascinating world of Group 14.
The elements, a spectrum of properties.
So first off, that striking diversity in metallic character. You've got carbon and silicon, clearly nonmetals. Then germanium, sort of in the middle as a metalloid. And then tin and lead are definitely metals. What's driving that big shift down the group?
Right. It's actually one of the most reliable trends you see in the P block of the periodic table. Metallic character increases as you go down. Always. And it comes down to basic atomic properties. As you descend the group, the atoms get bigger, the atomic radius increases, and crucially, the energy needed to remove an electron, the ionization energy, goes down. So for the heavier ones, like tin and lead, it's just easier for them to lose electrons and form those positive ions, allocations. That's what gives them their metallic nature.
Okay, that makes sense. Now, thinking out their electrons, they have that ns²np² configuration in their outer shell. That usually suggests a +4 oxidation state is common, right?
Yeah.
But,
Generally, yes. For carbon and silicon, +4 is definitely dominant.
but lead. Lead is different, isn't it?
It absolutely is. For lead, the +2 oxidation state is actually the most stable and common one. And this is the classic example of something called the inert-pair effect.
Oh, the inert-pair effect.
Yeah. For these really heavy elements down at the bottom of the block, those 2's electrons in the outermost shell, they sort of become reluctant to get involved in bonding. They act almost inert, as the name suggests. So losing just the 2 p electrons to get to +2 becomes more favorable than losing all 4 valence electrons to get to +4.
So that effect fundamentally changes lead's chemistry compared to, say, carbon.
Definitely. It's a key takeaway. For heavy p-block elements, don't always assume the highest oxidation state is the most stable. Now, shifting gears slightly to chemical affinity. Carbon and silicon, their electronegativity is pretty close to hydrogen's. That's why you see countless covalent compounds with hydrogen, like hydrocarbons, and also with alkyl groups. They're also what chemists call oxophiles and fluorophiles.
Meaning they like oxygen and fluorine.
Exactly. They have a strong affinity for hard anions like oxide, O2, and fluoride, F. Think carbonates, think silicates, they're everywhere in nature. But contrast that with lead. It's considered a chemically soft element. It prefers to bond with soft anions, things like iodide or sulfide, S2. It forms more stable compounds with those. So different bonding preferences entirely.
Hard likes hard, soft likes soft. A fundamental chemical principle.
You got it.
Simple compounds, fundamental building blocks.
Okay, let's move on to some simpler compounds, hydrides, for instance. All group 14 elements form EH4 molecules, like methane, CH4. But carbon does something really special here, catenation. Can you explain what that is?
Catenation is just the ability of an element to bond to itself, forming chains or rings. And carbon is, well, it's spectacularly good at it, uniquely good. That's the basis for the absolutely vast world of organic chemistry, all those hydrocarbons, like alkanes, with long carbon chains.
Why is carbon so good at it?
2 main reasons. First, the carbon-carbon single bond is very strong. Carbon-hydrogen bond is also very strong. High bond enthalpies, meaning they take a lot of energy to break, so the chains are stable. Second, carbon is also great at forming strong multiple bonds, double bonds in alkenes, triple bonds in alkenes. That adds another layer of stability and reactivity options.
Right. Organic chemistry basically hinges on that.
Pretty much. But this tendency for catenation, it really drops off as you go down the group.
So silicon doesn't form long chains like carbon.
Not nearly as well. Silicon forms silanes, which are the silicon analogs of alkenes like Si4, Si2H6, Si3H8, but the chains are much shorter. I think the longest confirmed one is only heptasilane Si7H16, and they're way more reactive than alkenes.
More reactive. Why is that?
Well, a few things. Silicon atoms are bigger than carbon, so the Si-Si bond is weaker and longer, more exposed. The Si-H bond is also more polar than CH. And critically, silicon has accessible low-energy orbitals.
Ah, the d orbitals.
Exactly. These can accept electrons from attacking molecules, like water or nucleophiles, providing an easy pathway for reaction. Carbon doesn't really have that option easily available in its valence shell. Just to give you a feel for the difference, propane, C3H8, is a stable gas we use in barbecues. Trizylane, Si3H8, is a liquid that boils at 53 degrees C and can spontaneously ignite in air. Very different characters.
Wow, okay, big difference. What about halomades, like reacting these elements with chlorine or fluorine?
Right, halones, carbon forms tetrahaldomethanes, like carbon tetrachloride, CCl4, or the very inert Teflon precursor, CF4. Their stability actually decreases a bit as the halogen gets heavier, from CF4 down to CI4. But the really crucial point is how they react with water hydrolysis. Carbon tetrahaloids are kinetically very resistant. They react incredibly slowly, if at all, under normal conditions.
And that's not the case for silicon and germanium halides.
Not at all. Silicon tetrachloride, so Cl4, and germanium tetrachloride, GgEC4, hydrolyze extremely rapidly, often quite violently with water.
What's the underlying reason for that dramatic difference?
It goes back to those available d orbitals, or just the ability to expand the coordination sphere. Silicon and germanium can easily accommodate a fifth or even sixth group bonding to them temporarily. They form what we call hypervalent intermediates. Imagine water attacking CCl4. Silicon can accept the electrons from water's oxygen, forming a temporary 5-coordinate species, which then easily kicks out a chloride ion.
And carbon can't do that easily.
Nope. Carbon is pretty much stuck at 4 bonds in these simple compounds. It lacks those easily accessible orbitals to form that intermediate. So the reaction pathway is it does. Tin can form both aldehydes, like SnCl2, and tin tetrahydrides, like SnCl4. But for lead, because of that strong inert-pair effect, only the lead dihydes, like PbCl2 or PbI2, are really stable. The tetrahalides are very unstable or don't exist. And interestingly, these lead dihydes often have distorted crystal structures. We think that lone pair of I's electrons on the lead-2 ion is stereochemically active. It takes up space and pushes the bonds around, distorting the geometry.
Fascinating. Okay, how about oxides? Carbon gives us CO and CO2, which are fundamental molecules.
Right, carbon monoxide, CO, with its very strong triple bond, and carbon dioxide, CO2, with its double bond, small, discrete molecules. But silicon's relationship with oxygen, that's a whole different story.
How so?
Silicon has an incredibly high affinity for oxygen. It loves oxygen. This leads to the formation of the huge variety of silicate minerals that make up most of the Earth's crust, plus many synthetic silicon-oxygen materials. The fundamental unit here is the IO44 tetrahedron. Imagine a silicon atom in the center bonded to 4 oxygen atoms at the corners of a tetrahedron. Okay, got a picture.
These tetrahedra then link together by sharing oxygen corners in countless ways. They can be isolated, orthosilicates, linked in pairs, disilicates, form chains, sheets, or complex 3D networks. This linking ability is key to the diversity of silicates.
And this links to everyday materials, like glass.
Absolutely. Common glass is primarily made from silica, which is silicon dioxide, SiO2. In silica, those SO4 tetrahedra are linked into a vast, irregular 3D network. Glass is interesting because it's an amorphous solid. It has short-range order, the tetrahedral units are there, but no long-range, repeating crystal pattern like quartz. It behaves like a solid, but has a structure somewhat like a supercooled, extremely viscous liquid.
So it flows, but incredibly slowly. Effectively, yes. Though over human timescales, it's definitely solid. And for the heavier elements, germanium, tin, lead, they also form oxides. Again, the inert pair effect makes the +2 oxidation state more stable lower down, so you get GO, SNO, PBO, as well as the +4 oxides like GO2 and SNO2. Lead even forms mixed valence oxides like red lead, Pb3O4, which actually contains both lead-2 and lead ions in its structure.
Carbon's allotropes in extended forms more than meets the eye.
Okay, this next part is where, for me, it gets really interesting with carbon. The allotropes, different forms of the same element, diamond and graphite. They're both pure carbon, but couldn't be more different. How does that work?
It's one of the most striking examples of how structure dictates properties. It's all about how the carbon atoms are bonded together. In diamond, every single carbon atom is bonded to 4 other carbon atoms using strong single bonds. These are arranged tetrahedrally. This creates an incredibly strong, rigid, 3-dimensional network extending throughout the crystal. That's why diamond is the hardest natural substance we know. It's also an electrical insulator because all the valence electrons are locked up in those localized single bonds. It is, however, a great thermal conductor.
Okay, so rigid 3D network equals hardness and insulation. What about graphite?
Graphite is completely different. It's made of flat sheets, or layers. Within each layer, which we now often call a graphene sheet, each carbon atom is strongly bonded to only 3 other carbons in a hexagonal, honeycomb-like pattern. They use what we call sp2 hybrid orbitals for these strong sigma bonds within the plane, but each carbon still has one valence electron left over.
And what happens to that electron?
These leftover electrons form delocalized pi bonds that spread out across the entire sheet. It's like a sea of mobile electrons moving within each layer. And that is why graphite conducts electricity very well, but mostly parallel to the layers.
So the electrons move along the sheets.
Exactly. And the forces between these stacked layers are much weaker, just van der Waals forces. So the layers can slide past each other easily. That explains why graphite is soft, slippery, and used as a lubricant. Totally different properties arising just from arranging the same atoms differently.
Mind-blowing, really. And you mentioned before, diamond technically wants to turn into graphite, but it's just incredibly slow.
Yes, thermodynamically graphite is slightly more stable under normal conditions, but the activation energy to break all those strong bonds in diamond and rearrange them is enormous. So thankfully, diamonds are practically forever.
Good to know. Now, you mentioned graphite's layers. Can things get in between them?
They absolutely can. Graphite forms what are called intercalation compounds. Because the layers are held by weak forces, other atoms or molecules can slip in between the graphene sheets. For example, alkali metals like potassium can slide in. Potassium atoms donate their valence electrons to the graphene sheets, forming compounds like Kc8. This actually increases the electrical conductivity because you've added more charge carriers.
Interesting. Does it work the other way, taking electrons out?
Yes, you can react graphite with strong oxidizing agents, like sulfuric acid and nitric acid mixtures. These pull electrons out of the graphene sheets, forming things like graphite bisulfates. This also increases conductivity, because now you have positively charged holes that can move through the layers. There's even a phenomenon called staging, where the intercalated species don't go between every single layer, but maybe every second layer or every third layer in a very ordered pattern.
Wow. Okay, moving beyond diamond and graphite, the late 20th century brought us a whole new world of carbon forms, right? The fullerenes.
That's right. Discovered in the 1980s, these were a huge surprise. The most famous is Buckminster fullerene, or C60, which has that iconic soccer ball shape.
Buckyballs.
Exactly. They're typically formed by creating an electric arc between graphite electrodes in an inert gas like helium. The soot produced contains C60, C70, and other larger fullerenes. Their structure is based on closed cages made up of interconnected 5-membered and 6-membered carbon rings. C60 has 12 pentagons and 20 hexagons.
And they have some pretty advanced properties, too.
They do. If you react fullerenes with alkali metals, you can form fulleride salts like K3C60. These are fascinating because they can be metallic conductors, and some even become superconductors at relatively high temperatures for superconductors, while still very cold. And closely related are carbon nanotubes. You can think of these as sheets of graphene rolled up into seamless cylinders. They can be single-walled or multi-walled, like concentric tubes. Nanotubes are incredibly strong, great electrical conductors, and have huge potential in areas like electronics, materials science, maybe even hydrogen storage and catalysis.
And then there's graphene itself, the single layer.
Yes, isolating single sheets of graphene only became feasible much more recently, around 2004. It has phenomenal properties, amazing electrical conductivity, incredible strength for its weight, but making large defect-free sheets consistently and cheaply is still a major challenge.
So we've got diamond, graphite, fullerenes, nanotubes, graphene. Are there other important forms of carbon? Maybe less. Perfectly structured.
Definitely. There are many commercially important forms of carbon that are less crystalline, more amorphous, or disordered. Carbon black, for instance, is a fine powder produced by incomplete combustion of hydrocarbons. It's used extensively as a black pigment in inks and paints, but its biggest use is as a reinforcing agent in rubber, especially for vehicle tires. It makes them much stronger and more durable.
Right, you see that on tires.
Then there's activated carbon. This is carbon treated to create lots of tiny pores, giving it a huge internal surface area. This makes it an excellent adsorbent.
For filters and things.
Exactly. Water filters, air purifiers, gas masks, they often use activated carbon to trap pollutants and impurities. And finally, carbon fibers. These are produced by heating precursor organic fibers to high temperatures to carbonize them. They are lightweight but incredibly strong and stiff, especially along the fiber axis. They're used to reinforce polymers, creating high-performance composite materials for things like aircraft parts, high-end sports equipment, racing cars. Anywhere, strength-to-weight ratio is critical. So yeah, carbon's versatility is just immense.
Silicon's extended network compounds shaping our environment and technology.
Okay, let's switch back to silicon now. We talked about simple silicates, but things get even more complex and diverse with aluminosilicates. What happens when aluminum gets into the mix?
Right, this is where the structural diversity really explodes. Aluminosilicates are formed when some of the silicon atoms in the silicate framework are replaced by aluminum atoms. Now remember, silicon is typically Si, meaning it has a +4 charge state in these oxides. Aluminum is typically Ul3 with a +3 charge.
So swapping an Al3 for Nc leaves a negative charge behind on the framework.
Precisely. Each substitution creates 1 unit of negative charge on the overall aluminosilicate framework. To keep the whole material electrically neutral, you need extra positive ions, cations, incorporated into the structure. These charge balancing cations could be simple ions like sodium, Dam+, potassium, K+, calcium, Ca2+, or even protons, H+. And the presence and type of these cations dramatically influence the properties of the material.
What are some common examples in nature?
Oh, they're incredibly common. Think of clays, talc, micas. These are all layered aluminosilicates. For instance, kaolinite, the main component of China clay, is a relatively simple, layered structure. Interestingly, it's used medically to help blood clot, likely due to its surface properties. If you look at the structure of talc, which chemically is Mg3OH2Si4O10, the layers formed by the silicate sheets sandwiching a magnesium hydroxide layer are actually electrically neutral overall.
And that's why it feels slippery, because the layers slide easily.
Exactly. There are only weak van der Waals forces between the neutral layers, so they cleave very easily. Contrast that with a mica like muscovite, Kal2OH2Si3LO10. Here, 1 out of every 4 silicon sites is replaced by aluminum. This creates negatively charged layers. Those negative charges are balanced by potassium ions, K+, sitting between the layers. These ionic interactions hold the layers together more strongly than in talc. So mica is harder, but still cleaves into sheets because the bonding is weaker between the layers than within them.
Okay, so layers. Are there 3D structures too?
Absolutely. Feldspars are a hugely important class of rock-forming minerals. They have 3-dimensional aluminophilicate frameworks. These frameworks have cavities or channels within them that can accommodate larger cations like potassium K+, sodium Na+, calcium Ca2+, even barium Bb2+. The specific framework and the cations present define the different types of feldspar.
Now, within these aluminosilicates, there's a really special group called zeolites. They're sometimes called molecular sieves. What makes them stand out?
Zeolites are crystalline aluminosilicates, but what makes them unique is their highly porous structure. They have networks of interconnected cavities and channels, often with openings or apertures, of very precise, uniform sizes, typically on the scale of small molecules.
Molecular sieves, so they can filter molecules based on size.
That's exactly right. They can selectively absorb molecules that are small enough to fit into their pores while excluding larger ones. This makes them incredibly useful.
What kind of applications do they have?
A huge range. One major use is as ion exchange resins. The charge balancing cations within the zeolite framework, like Na+, are often mobile and can be swapped out for other cations. This is used in water softening, for example. Zeolites in detergents can trap calcium and magnesium ions from hard water, swapping them for sodium ions, which prevents scum formation. They were a key replacement for phosphates, which caused environmental problems in waterways.
Okay, that makes sense.
Another massive application is in catalysis, particularly shape-selective heterogeneous catalysis. Because the reactions happen inside those precisely sized pores, zeolites can control which reactant molecules can get in and sometimes which product molecules can form and get out. A famous example is the zeolite ns²np², used in the petroleum industry to synthesize specific isomers of xylene, which are valuable components of gasoline. It selectively produces the desired isomer because of the shape constraints within its pores.
Can you give us a picture of their structure?
Many zeolites are built up from a fundamental cage-like unit called a sodalite cage, which looks like a truncated octahedron. Imagine a shape with square and hexagonal faces. These cages then link together in different ways, sharing square faces or hexagonal faces, or linking via oxygen bridges to create larger, more open structures with interconnected channels and larger central cavities, sometimes called supercages. The charge balancing cations like NAP+ reside within these cages and channels.
It really sounds like nanoscale architecture. You mentioned that ship-in-a-bottle idea, too.
Yeah, that's a neat concept sometimes used with zeolites. You might be able to get small reactant molecules into a cage, have them react inside to form a much larger molecule, which is then physically trapped because it's too big to get out through the pores.
Clever. Okay, shifting slightly within silicon chemistry, what about compounds with silicon bonded directly to carbon? Organosilicon compounds.
Yes, the carbon-silicon bond, CSI, is actually quite strong and stable. This allows for a whole field of organosilicon chemistry.
And the most well-known application is probably silicones.
Definitely. Silicones, more formally called polysiloxanes, are polymers that are incredibly important industrially. They're typically manufactured starting from methylchlorosilane.
What's their basic structure like?
Their defining feature is the polymer backbone, which consists of alternating silicon and oxygen atoms, COCOSI. Attached to the silicon atoms are usually organic groups, most commonly methyl groups, CH3.
So it's not a carbon backbone like in polyethylene or PVC?
No, it's fundamentally different. It reflects the great strength and stability of the silicon-oxygen bond compared to the silicon bond. That Si-O-Si linkage is key.
And what kind of properties do silicones have? They seem to be used for everything.
They're incredibly versatile. Their properties can be tailored dramatically. They can be oils, liquids, rubbery gels, or hard resins depending on the length of the polymer chains and the degree of cross-linking between chains. Generally, they are very stable to heat and oxidation. They are hydrophobic, water repellent. They have low surface tension, and their viscosity changes relatively little with temperature compared to hydrocarbon oils.
Which makes them good for?
Lubricants, especially in demanding conditions. Sealants and adhesives, think bathroom caulk. Waterproofing sprays for fabrics and masonry. Release agents so things don't stick in molds. Even in cosmetics and personal care products like shampoos and conditioners, where they provide that smooth, silky feel, they're everywhere.
Wider impact industrial uses and environmental concerns.
Okay, let's broaden the scope now to the wider impact of Group 14 elements, energy, industry, and some significant environmental and health issues. Let's start with something called methane clathrates. What are they?
Methane clathrates, sometimes called methane hydrates, are fascinating structures. They're essentially crystalline solids where methane molecules, CH4, are trapped inside cage-like structures formed by frozen water molecules, ice. They form under conditions of high pressure and low temperature, typically found on deep ocean floors and buried in permafrost regions, and there are vast quantities of methane locked up in these clathrates globally.
So potential energy source, but also a risk?
Exactly. It's a dual perspective. On one hand, the sheer amount of methane stored makes them a potentially enormous future energy resource if we could extract it safely and economically. On the other hand, there's a significant environmental concern. Methane is a very potent greenhouse gas, much more so than CO2 over shorter timescales. If these clathrates become unstable, perhaps due to warming ocean temperatures or melting permafrost, large-scale release of this methane into the atmosphere could dramatically accelerate global warming.
Could it cause other problems too?
Yes. There's also concern that destabilization of clathrates on continental slopes could trigger submarine landslides, potentially leading to tsunamis. So they're both a promise and a potential peril.
Okay, switching to more conventional industrial uses, what about things like silicon carbide?
Silicon carbide, C, often known by its trade name carborundum, is an extremely hard refractory material. It's structurally related to diamond. Its main use is as an abrasive for grinding wheels, sandpaper, cutting tools. It's also used in high-temperature applications like furnace linings and ceramics.
You're 10.
Yeah.
You see it coating steel cans.
Right. Tin plating on steel, tin cans, is a classic use, providing corrosion resistance, especially against food acids. Tin is also a key component of alloys like bronze, copper tin, and pewter, and crucially, solder, used for joining electronic components and pipes.
Okay, now for the less positive side toxicity. Some Group 14 compounds are notoriously dangerous.
Tragically, yes. Hydrogen cyanide, HCN, and its salts containing the cyanide ion, CN, are extremely toxic and very rapidly acting. They work by inhibiting a crucial enzyme called cytochrome C oxidase, which contains iron and is vital for cellular respiration in mitochondria. Basically, they shut down the cell's energy production, leading to rapid collapse.
And carbon monoxide, COO.
Carbon monoxide is also highly toxic, but by a different mechanism. It binds very strongly, much more strongly than oxygen, to the iron atom in hemoglobin, the protein in red blood cells that transports oxygen. By binding to hemoglobin, CO prevents oxygen from being picked up in the lungs and delivered to tissues, effectively causing chemical suffocation.
What about organometallic compounds, like with tin?
Organotin compounds, particularly tributyltin, TBT, were widely used for decades as biocides, especially in anti-fouling paints for ships' hulls to prevent barnacles and algae growth. However, it became clear they were leaching into the marine environment and were extremely toxic to marine life, causing developmental problems in shellfish, like oysters, even at very low concentrations. Their use is now heavily restricted globally due to these severe environmental impacts.
And the story of lead in gasoline is another major environmental health issue, right?
A huge one. Tetraethyl lead, PbC2H54, was added to gasoline for decades as an anti-knock agent, improving engine performance. But lead is a heavy metal neurotoxin. Burning leaded gasoline released vast amounts of lead particles into the atmosphere, leading to widespread environmental contamination and significant public health concerns, particularly regarding the effects of lead exposure on children's neurological development and IQ.
And thankfully, it's been phased out in most of the world.
Yes, the phase-out of leaded gasoline is considered a major public health success story. But the problem of lead exposure isn't entirely gone.
How so?
Lead persists in the environment. Major sources today include old lead-based paint, especially deteriorating paint in older housing, which can create contaminated dust that children ingest. Old lead pipes used for drinking water supply can also leach lead into the water.
And how does lead affect the body, especially children?
Lead-2 ions, Pb2+, are chemically similar enough to calcium ions, Ca2+, that the body can mistake them. Lead can get incorporated into bones and teeth, accumulating over time. In children, even low levels of lead exposure can cause irreversible damage to the developing brain and nervous system, leading to learning disabilities, behavioral problems, lower IQ, and impaired growth in hearing. It's a serious and persistent public health challenge.
Which really brings us full circle back to carbon and its global impact via the carbon cycle and climate change.
Exactly. The natural carbon cycle involves the exchange of carbon between the atmosphere, oceans, land, and living organisms through processes like photosynthesis, which removes CO2, and respiration and combustion, which release CO2. For millennia, this cycle was roughly in balance. However, since the Industrial Revolution, human activities, primarily the burning of fossil fuels, coal, oil, natural gas, for energy, along with deforestation and other land use changes, have been releasing enormous amounts of extra CO2 into the atmosphere much faster than natural processes can remove it.
And this leads to the greenhouse effect.
Precisely. CO2 is a greenhouse gas. It traps heat in the atmosphere, leading to a gradual warming of the planet, global climate change, with all the associated consequences like rising sea levels, more extreme weather events, and ecosystem disruption. Disrupting the carbon cycle is arguably one of the biggest challenges humanity faces.
Are there technological approaches being explored to mitigate this related to Group 14 chemistry?
One area being actively researched is carbon dioxide sequestration, or carbon capture and storage, CCS. The idea is to capture CO2 emissions from large print sources like power plants or industrial facilities, prevent them from reaching the atmosphere, and then store the CO2 long-term, typically by injecting it deep underground into suitable geological formations.
So trying to put the carbon back where it came from, in a sense.
In a way, yes. It's a complex and costly technology with its own challenges, but it's considered one potential tool among many needed to reduce atmospheric CO2 concentrations. Outro.
Wow. Okay, so we've really covered a huge amount of ground today. From carbon, the absolute basis of life, and silicon, shaping our planet's rocks and enabling our technology, through the properties of germanium, tin, and lead, they're complex compounds, amazing structures like diamond, graphite, zeolites, silicones, and their profound impact, both positive and negative, on industry, health, and the global environment. It's quite a story for just one group.
It really is. And hopefully you can see how understanding some core chemical concepts, things like metallic trends, the inert-pair effect, carbon's unique catenation ability, the way silicon forms extended networks with oxygen, the structure of allotropes, how these ideas help us make sense of why these elements behave the way they do. It lets us understand their roles in nature and how we can harness their properties for technology, but also appreciate the risks and responsibilities involved.
Absolutely. And it leaves you thinking, as our ability to manipulate matter at the atomic level grows, as we design new materials and understand Earth systems better, what new ethical questions arise? What responsibilities do we have regarding these fundamental elements that literally make up our world? definitely some food for thought.
Indeed.
Well, thank you so much for joining us on this deep dive into Group 14. And from the whole last minute lecture team, thanks for listening.